Yeah, thanks. Yeah, we already heard the name RISC-V several times today, and I had very nice conversations about RISC-V in general. And yeah, now I'd like to get a bit more into detail with this talk. So let's start with an overview what RISC-V is. At the core, it's a 32-bit reduced instruction set with around 40 instructions in 6 formats. And because it's pretty simple to implement, you can build an interpreter in almost an afternoon. Yeah, there are several examples on Hackage. The whole thing is augmented by many extensions. So extensions are part of the concept. And the whole instruction set feels a lot like playing with Lego bricks. So you just stick one extension into another extension, and finally you get the whole thing. And custom extensions, even closed source ones, are anticipated by the instruction set. We actually had one master student reaching out at the GHC mailing list that was exactly after that who asked if we can't find instructions that would help GHC to produce faster code. So that's actually part of the game. And that makes it an ideal research vehicle for computer architectures. The whole ISA is open source. Implementations can be closed source, can be under any license. The instruction set is under Creative Commons. It's developed on GitHub. It has a very vibrant community. The more advanced conceptualization part is done in working groups at RISC-V International. And yeah, membership is free for individuals, so anyone can join. Yeah, and everybody is free to build a RISC-V processor. So there are many vendors. Hobbyists do it, create emulators, interpreters, or even tape out their designs on Tiny tape out, for example. That costs a couple of $100, of course, with bigger structural width. But yeah, I guess it's a lot of fun and probably very educative. The current status is the standard feels pretty complete from my perspective. So there are lots of documents describing the instruction set, the calling convention, and so on and so on. Most important part, Linux runs. What's a bit of a pain is currently there's still a lack of powerful hardware. Yeah. That's why we got no high-performance cloud options. Even though there are some cloud options, they're usually not high performance. So yeah, we can't have native cloud CI in our GitLab CI as GHC developers. That's a bit painful currently. Most other projects are using some mixture of Docker and QEMU to emulate in CIs, but that's way too slow for us. Just as an example, the cores are currently comparable to older ARM cores. For example, the LigiPi 4a that I am using is advertised as being comparative to Raspberry Pi 4b. That's now a couple of years old. So yeah, we are lagging a couple of years behind, and even your smartphone might be more powerful than current RISC-V SPCs. So there's lots of movement. New boards and chips appear pretty frequently. There are many manufacturers, and research started all over the world. The EU created a big grant for RISC-V high-performance computing research. It's a DARE project, Digital Autonomy with RISC-V in Europe, with a funding of 240 million euros. India has something similar with their Shakti CPU. I don't have any figures about the funding, but yeah, that's also pretty impressive. And I'm under the impression that other universities on other continents are just keeping up. Yeah. Now, yeah, here be dragons. This is a new architecture. So some tools don't support the full instruction set. As I told you or explained, new instructions are partly kind of the game, so that's not surprising, but it can sometimes be annoying that tools always have to catch up. Tools sometimes have still bugs. I experienced that, for example, with vectors on QEMU, where a newer version magically solved some issue I had. And yeah, the cores are pretty new. I haven't experienced any bugs with my cores at home, but there aren't probably not that many users, so yeah, I'm not sure if you really want to put a big bug on RISC-V cores. And some cores may not adhere to the ratified standards because they are a bit older. That can also be a bit annoying. So yeah, my advice would be to use the latest releases and be very precise about the hardware and the build target. That's why I included a slide to explain how build targets are described. So this can matter when you create bug reports, for example, to just very specifically explain what you are building for. This looks pretty crazy, right? But there are some reduction rules that make it a bit easier to grasp. So the whole thing starts with the base ISA. In our case, this will always be RISC-V 34 bits. Then there are extensions. Those are identified by the first letter. And extensions can be versioned, but don't have to be versioned. So you can have that this string here just strings together by not having these versions. And then there are sets of versions like this G. That's G for general. This implies, for example, integer arithmetics and atomic operations, floating point operations, and so on. And some extensions imply other extensions. So if I want to do multiplication with the multiplication extension, then I also need some lower level multiplication extension. So far, so clear? And yeah, because that might be a bit confusing, we can add a bit more confusion to that. There are also profiles. That's basically a way to not have everybody to deal with these crazy string we saw before, but to define some minimum requirements. I don't know. If you remember from the past, maybe Intel Pentium, that was something, and you knew when you buy software that this runs on Pentium, for example. And these profiles are in a similar manner. What's a bit unfortunate, this concept is a bit new, and it's not commonly used by vendors. So yeah, it's sometimes still a bit of guesswork, try and error game. How Linux distributions deal with that is by usually sticking to a very small extension set. Usually just the general ones and compressed instructions. Okay, now to our implementation status of RISC-V support. Now to the GHC RISC-V history. The first thing that landed was the LLVM backend back in 2020 in GHC 9.2, mostly done by Andreas Schwarz. Then 2023, Moritz and I accidentally started implementing a native code generator backend for this at the same time. Then Moritz switched over to some kind of a mentor role that was very, very helpful, and it's probably not by accident that the RISC-V backend looks very similar to the ARM-64 backend. I continued to hack. Andreas Schwab created some kind of a CI with the build tools at SUSE. They've got some build farm, and he eagerly created patches that could be used in this build farm to just have something that's similar to a CI. And the whole thing got merged last summer and is now part of GHC 9.12. And my super tip here, reach out, team up. Me, myself, I wouldn't have imagined that such a great collaboration would have been possible between former strangers, but indeed it is. That's kind of the magic of open source. Now, our current status of RISC-V support in GHC. As said, we've got the LLVM backend, we've got an RTS linker for static linking working. We've got the native code generation backend that fulfills the whole test suite, minus SIMD tests, because that's a new feature and I have to still catch up. And we are targeting the general extension, or general and compressed in case that the toolchain just reduces bigger instructions to those compressed instructions. That can just magically happen by optimizations in the assembler, for example. SIMD support is still work in progress. I hope to get it done at Zurihac. It's pretty far, you will see. And as Ben already mentioned, this is a tier 3 platform. We don't have powerful enough hardware to create binary distributions in our CI, and can't really run the tests there. So this will stay probably a tier 3 platform for quite a while. I'm not sure. I'm looking at Ben. And it's probably not much in use yet. I think things will become more interesting the more packagers or Linux distributors start to package for RISC-V and start to use newer GHC versions. But I'm very happy to receive bug reports. It's usually better to fix things early than later when too many people start to complain.
Is it a cross-compiler at the moment, or have you bootstrapped?
Is there a cross-compiler?
Is there a cross-compiler from x86 to RISC-V, or do you have a native binary that runs on RISC-V?
Both. So,
repeat the question.
So Matt was asking if we've got a cross-compiler from any architecture or x86 to RISC-V, and yes, GHC has cross-compiling features. I'm using that a lot during development. However, it can also be bootstrapped with the LLVM backend on the native hardware.
Okay. Cool. Yeah, okay.
I hope that answered your question.
Yeah, I forgot about the LLVM backend.
Because I remember you worked a bit on cross-compilation lately, and that's why I wasn't sure. It's not more advanced questions. So let's look at SIMD or vector support. That's now ongoing work. I think that's more interesting. Future. So RISC-V tries to solve vector problems a bit differently than other architectures. And the problem is usually that applications need very different vector sizes, and chips need very different vector sizes. So embedded chips should save silicon. High-performance computing chips may need big vectors because you need them for weather calculations or such things. And then there's usually a trade-off where vendors try to find some common ground and put that into one standard or one processor extension or one processor feature, however you call it. But finally, in these cases, the maximum vector sizes are bound to specific ISA features. What RISC-V now does is to allow dynamic reconfiguration of vector sizes. So you can finally get from the smallest 32-bit register sizes for vector registers to 65,000 bits per vector register. That's a pretty great range. And I thought that's so exciting that we can even dive a bit more into this topic. So basically there are two ways to tackle this issue, to be so flexible. One way is to make the effective register width configurable by grouping. So to say, or to ask the question, if one vector register isn't big enough, can't I use 2 for my calculation, or 4, or more, maybe? And the other one is to do some kind of strip mining. So let the machine tell my program, okay, I couldn't give you such a big vector, but a smaller one, and then you can loop over smaller chunks.
You've got about 7 minutes with questions.
Oh, wow.
8 minutes with questions.
Then we have to hurry a bit. Yeah, right. That's basically where the magic happened. That's the assembly instruction where I can configure my vector size. So as a result, I always get the new effective vector size in elements. Then as a first parameter, I can request a specific vector size as user or as application. Then I define the size of the elements and some multiplier for exactly this grouping that I tried to explain. So, okay, I'm hurrying.
What's the most interesting thing, Sven?
What's the most interesting?
Focused on that.
What's the most interesting thing? I thought this was the most interesting thing.
You've got 20 more slides. You know.
Oh, I've got backup slides.
Oh, I see. This is very interesting. Sorry.
So for this simple task, I tried to explain this here with C code. Yeah, here I've got some thing that could be explained as a vector that's basically incrementing on an array. That's basically the classical example. And the point is that in this case, I would need a smaller vector group because 8 times 8, if I want to have an 8 times 8 big vector, is 64, and I've got 128-bit register width. So I'm just configuring here that I want to have 8 elements, and I've got some group that tells me I only want to have half the size of the register. And then the same thing, if I want to have a bigger one, 16, then I need the full register width, And then I can say, okay, give me the whole group, or give me a group of one register. And I can play this game even further. If I want to have 32 elements that would not fit into my one vector register, then I can have a group of two registers. And I think we can, let's skip the strip mining then. And
You got 5 minutes with questions.
5 minutes with questions. Okay. So then maybe hard to decide. Vectors, yeah. So the questions that this raises are basically if you can have such vector register groups, how to map them to what we already got in GHC for vector allocations. And the obvious question, do we even want to have that?
We kind of had this on 32-bit for 64-bit values.
Ah, okay. That's an interesting hint. I didn't know that.
Maybe not the best design.
So that's a good question. And if we, or another thing, do we want to go into the strip mining approach that I now skipped out of timing reasons? Basically looping over elements. And would that work for all our machine operations? Yeah, open questions. Just as a note, the first edition that will hopefully be merged soon will have none of this, but just expect that the register size is big enough. Otherwise it will panic, and the user has to define what he or she wants to see in their code. Okay, let's maybe skip that. And have a couple of more general future tasks. What we could do is investigate standard extensions beyond this general and vector extensions. Good candidates maybe the B extensions for bit manipulation, or the Z-cont extensions for integer conditional operations. We could teach GHC to understand this crazy machine string we saw before, because this might make configuration a bit more natural to people used to other tool chains. And we could also try to use GADTs, that's more a general one, for instructions in our native code generators to make them more type safe. And I call this pattern a bit pattern match or panic.
Oh, instructions, not mockups. You mean really instructions then?
Yeah, the instructions we create for each native code generator.
I see. Okay.
And these are usually held pretty general. And maybe we can do a bit more with some type constraints or so. Okay, and because I'm out of time, I would stop here now. Okay, let's start with Rodrigo.
So I'm wondering, how would you see the fact that you can reconfigure the length of the vector register in RISC-V being mapped onto the Haskell level construct? So currently, GHC already supports SIMD vectors, in master at least. And are those reconfigurable length? And if not, how do you envision that being part of the user-facing API primitives?
Oh, that's actually that's actually a question I wanted to raise.
Maybe you can repeat the question for the camera.
So the question was, if I got it correctly, as the RISC-V architecture has reconfigurable vectors in size, how to map that to GHC internals. And I'm not sure, but I'd be happy to discuss. Matt?
So I don't know the particulars of the instruction sets, but my impression is that long arch is similar to the Chinese version of RISC-V. Is that about right? Do you know any more? Do you have a more like insightful insight into the difference between the two?
Oh, I don't know much about long arc, but I haven't heard that it would be really compatible. So probably the instruction sets may look similar because they are both rooted in this RISC architectures, reduced instruction sets, but they are not the same. And I haven't seen it mentioned anywhere in the same sentence or so.
Long is derived from MIPS, I think. So they are a bit different.
But maybe similar in spirit, but not not really compatible.
We can take one more question.
Ben?
Yeah, I was wondering, so often when you see these vector extensions, they seem to be really targeting, even more so than SIMD in ISAs, like sort of a, give me an array of a very large array of data, and I want to do a homogeneous operation across that entire array, right? Yeah. And so that you get the most bang for your buck, because you can then just say like, oh, yeah, well, I have 256 element wide vector. Just I can do very few instructions and get the decoding benefit over those very few instructions for a very large array. And I wonder, given that we only have like up to 256-bit wide vectors really usable right now, whether do you know, have other compilers used this ISA, the V extension, in this way of like just setting a static fixed 256 wide or 3 element or whatever, right? Vector length, and then just using it as a SIMD instruction set, or is that something that others have done? Or because I wonder if there's how much performance we're going to get there. Given that I think it's generally intended to be.
Performance-wise, it's a bit hard to say. LLVM expects or has some default vector length, and you can override it. That's currently part of their strategy. Okay,
but if you ask for like a 256, an 8-wide I8 vector in LLVM-IR, then it will lower to a V vector operation, I guess.
Yeah, maybe we should take that offline.
Let's take a speaker.
Okay.